theory of choking under stakes-based cognitive stress. Usual things to say. We are hosted by the University of Reading. We're sponsored by the Sports Economics Review, a great home for your manuscript in sports economics. Please do keep your microphones on mute. James and Sanders, Shane, are you happy taking questions as you go along, or would you rather have questions at the end?
If questions pop up as we go along, I'm okay with taking them in the process. That's fine with me.
Okay, so folk will probably all raise their hands, and if you see it, fine. If you don't, I'll then interrupt you.
Yeah. Flag me down if I'm moving past them. Yeah, sorry about that.
Great. Well, in which case, please do take away your talk, James.
Okay, are my slides displaying? Gotcha.
Yeah,
Okay. Great. So thanks everyone for being here. This is joint work with Shane Sanders, who's at Syracuse and currently here for support, and also Seifi, who's at Western Illinois. So the paper is about, in general, performance under pressure, but we're going to apply it to sports settings, so hopefully it'll be palatable to this audience. And so just, the basic topic of choking under pressure has been pretty well explored, right? And so the idea is standard economic theory usually tells us, higher stakes, so more on the line, should lead to more effort, which in turn leads to more performance, right? That's the standard or neoclassical version, incentives matter. But we know in many settings, some people, what we call choke under pressure. That is, when there's what we would call too much on the line, their performance declines. They don't do as well because of a variety of reasons. And so this phenomenon has been pretty well documented, again, in a variety of settings. There's a lot of examples from, standardized testing, job interviews, which, are important, but of course, sports are a very popular way to explore this phenomenon because, it's a very high stakes environment. And of course, we have data. And so what we're going to do here is we're going to explore the phenomenon of choking, but we're going to emphasize the non-monotonicity of the relationship, or maybe I should say potential non-monotonicity, because our point is going to sort of be that, more pressure can have all sorts of effects, and we're going to end up showing it's got some perhaps previously unexplored curvature to it. But the more standard non-monotonic relationship between pressure and performance is very well known in the field of psychology, and it's known as the Yerkes-Dodson law, and I hope I'm pronouncing that correctly. And so the Yerkes-Dodson law, which goes back all the way to 1908, it essentially just says, look, if there's nothing on the line, right? If there's nothing that really matters when you're going in, when you're expected to complete a task, then, your performance will start out at a relatively low baseline. And at least for a while, as you increase the stakes, as you increase what matters to the person who's supposed to perform the task, their performance will increase initially, but at some point there's a peak, and beyond that peak, we start to see declining performance. And so, you can interpret that as initial boredom, and as you get more stressed about your performance, that at first motivates you, but then when it sort of builds up too much, eventually you get too worried about everything and your performance declines. And I think this part's interesting. I'm not sure it matters. Well, it matters a little bit for the rest of the paper, but the original experiment was actually on mice, seeing how well they performed in mazes using varying shock intensities. But they've done lots of, human experiments to verify this phenomenon in psychology. So this inverted U relationship, the hill-shaped relationship between pressure and performance, is pretty well known, and it's well established in the psychology literature. Now, we're not going to go too much into the why of, choking. Well, I don't know, maybe that's not the right way to phrase it. Okay, so psychology has a couple basic concepts of why choking happens, and there's no explicit answer. There are various neurobiological explanations for it, but in general, the two main theories of why people choke under pressure in psychology fall under the categories of distraction and explicit monitoring. So distraction theories of choking are something along the lines of, when there's too much on the line, I start overthinking everything, and I'm not thinking explicitly about the task at hand. I'm thinking about, other things that aren't necessarily relevant to my current motor skills. And so we can imagine, since we're using free throw data from basketball for our main sports application here, so that'll be a standard example. If I'm taking a free throw and the game's on the line, I may be thinking more about, if I miss, we'll lose, everyone hates me. And so, I get distracted about what I'm doing. And this is different from what are known as explicit monitoring theories, which essentially go in the opposite direction. Where now, if I'm at the free throw line and the game's on the line, I'm not just distracted. I might actually also, perhaps at the same time, even though these things seem to go in counter directions, I might be overthinking my mechanics, right? So I'm thinking, okay, where's my hand right on the ball? Where's my elbow? How hard? So it's in a way, again, they're counter to one another. It's almost I'm not focusing enough because I'm distracted, or maybe I'm, too focused on and I'm overthinking things. And I'm pretty sure, at least my impression seems to be from the psychology literature, both are at play to some extent in different environments. And that's why we tend to see heterogeneous relationships between pressure and choking. But the point is, both of these theories of choking are pretty well established in psychology, and we're going to incorporate them in a pretty clean, simple theoretical model that we're then going to apply or sort of investigate using data. Primarily in this talk, it'll be from NCAA basketball, but we also have some other examples as well. So, okay, getting into the literature, because as I'm sure many of the audience here knows, there is quite a bit of literature, in particular on choking in sports environments. So we know choking happens. We know that there are many times when athletes under more stressful or more important moments in games, they don't perform as well as they normally do in what we would call regular time. Now, the evidence that I'm going to, go through here, I think the overall takeaway is, choking varies. And it varies in part in the literature because measuring choking and what counts as pressure, what counts as performance varies from scenario to scenario and depending on what data is available. So that's partly, I think, what has to do with the varying results on the degree of choking that will occur. But there's also the fact that there's a lot of heterogeneity in terms of people and athletes performing, and so not all athletes will feel the same effects of pressure in every setting, which sort of makes sense. So one of the sports that seems to be most popular for testing the phenomenon of choking is golf. And of course, this is primarily because golf is, to a large extent, an individual task, especially if we focus, as much of the literature does, on putts, right? So not just your approach shots, but those all important putts when you're going for the hole on the green. They're very standalone tasks, right? So even when we're looking at evidence from professional golf, it's not a controlled experiment, but it's pretty close relative to many other sports. And so there is quite a bit of literature, again, mostly from psychology here. So those are those papers listed up toward the top here: Masters, Lewis and Linder, Baylock and Carr, where they set up isolated putting experiments. And, they have various ways of inducing distraction or monitoring, sometimes by having subjects count backwards in their heads while they're putting. Sometimes they record them, or they make them more self-aware. And the results are essentially that choking does occur. When people get more worried about what's on the line, their performance does seem to suffer. And I think my interpretation of this literature is that the mechanism seems to lean toward explicit monitoring, but that's my interpretation. And there are plenty of other studies that will disagree with that. But since this is a sports econ series, we're going to emphasize more the literature from actual, professional golf competitions. And there are plenty of papers that look at PGA Tour performance. So, Professional Golf Association. And again, the presence of choking depends on how you define pressure and how you define choking. And so, at least, I guess earlier on in the literature, there were a few studies that seemed to find no evidence of choking. And these are the Clark papers and Wells and Skowronski. And these papers essentially just, not arbitrarily, but they classify what they would consider high versus low stress scenarios. And for example, I believe one of the Clark papers just looks at scores in the third round of the PGA Tour event versus scores in the fourth round, where the fourth round is more consequential since that's the final day. And they find scores don't change very much, so that's evidence that there's no choking. And they do similar things where they compare, shots where the leader, or you're one off the lead or close to the lead. But again, these are sort of binary pressure situations, and the measurement of what counts as choking might be somewhat questionable because it might not be as precisely defined. I think one of the better papers, at least studying the impact or the presence of choking in golf, is the Hickman and Metz paper, which is in Journal of Economic Behavior and Organization. And I think this is a really cool paper, but again, that's my opinion. So what they do is they actually put a dollar value on final putts of major PGA Tour events. So they look at, again, final putts. I believe they're all on the 18th hole. So they're where things are on the line. And they compare the dollar value of what the player would receive based on where they place if they make a putt versus if they miss the putt. So they have a clear and continuous measure of how much pressure a player is under for a given putt, and it's a pretty clear definition of, okay, you're this, if it's a putt, they're plausibly capable of making it. So if they miss it in this context, we're going to consider that choking under pressure. And they do find that this is, I guess, maybe their headline result, but they have, of course, quite a few other nuances. But basically, a putt worth a little over $50,000 leads to a 1% decrease in the likelihood that a golfer will make a putt on that final hole. And what's particularly interesting for our results, because we're going to emphasize this heterogeneity later, is that the effect is strongest for putts from an intermediate range. So they do find a small effect of pressure on putts from under 5 feet from the hole, but I believe it's significant, but it's much smaller. Putts from 5 to 10 feet away, which are, moderate difficulty, they have the largest effect. And putts from further away actually show little to no effect. And so this is interesting because you can, they primarily relate this to, they feel that this comes back to distraction theories. They think players are more distracted on intermediate putts that matter more. And they also they reference the effect of confidence, right? Because if you're very close to the hole under 5 feet, then even if there's a lot of pressure, you're probably pretty confident you can put it out. It's not going to affect you very much. And sort of going the other way, if you're beyond 10 feet away, if you're further away, then maybe, there might be pressure monetarily for making the shot. But since it's a tougher putt, maybe psychologically your confidence isn't as impacted because you don't look maybe as bad for missing a longer putt. But when it's intermediate, that's when stress seems to be the strongest, or has the strongest effect. And they also find that players with higher earnings, which we can maybe interpret as higher ability, have a lower influence from the effect of pressure as measured by the monetary value of a putt. And this could be because those players are just more capable, they're more skilled. So the pressure, it's, their automatic reflexes are, less impacted. Or it could be that, the same amount of money doesn't have the same marginal impact on their stress. It could be either, but the important thing is, higher earnings players do seem less influenced by pressure. And also players players putting better within the tournament, so another measure of ability, seem less influenced by pressure. Now, we also have evidence from football, not American football. I went against the name, calling it soccer, but it's, soccer, European football, however you want to call it. There is a large literature of potential choking in penalty kick situations. And so penalty kicks can be during the game or, during penalty shootouts at the end of it, or at the finish of a tie game. So different studies look at different penalty settings. And so this first paper, I think it's Jourdain, Hartman, and Vujik, or I'm not probably not pronouncing that right, so I apologize. But they looked at teams who had either won or lost a previous game that went to penalty kicks, and then looked at their performance in a subsequent game. And so the idea was pressure is going to be, in this case, reflected by, if we lost the last game because we didn't, we lost on penalties, then maybe we feel more pressure this time because we didn't do a good job with it last time. And interestingly, they do find a significant effect. Teams that lost a preceding shootout did score they had a significantly lower shooting percentage in their subsequent game that went to a shootout. And in fact, they even had lower performance than just compared to teams that hadn't been to a shootout in the past. And you can also look at, and so this is evidence that choking does seem to happen in penalty kick situations. And I should mention penalty kicks, of course, they're not as maybe pure of a setting to measure choking. Some people might argue that, it's not just a single shooter's performance, since the goalkeeper does play a role, but there's a large literature showing that it's primarily the shooter. And so it's still a pretty clean, isolated task that the individual is performing here. And you can also look, there's public data on World Cup shootouts where you can compare what they call decisive kicks, which mean, the game is on the line. So if the game goes to penalties and the other team has, they've already scored enough to win if I lose this kick, or if, we win if I make this last kick. Those are what we call decisive versus non-decisive kicks in penalties. And it seems like there is a lower conversion rate when kicks are decisive, although that's not significant because there's not a whole lot of data from World Cups alone. But there is more evidence coming up. Now, another well-known paper, I think, is this AER paper by Apestegui and Palacios Huerta, who does a lot of research on penalty kicks and football. And they found a clear first kicker advantage in penalty shootouts. And they attribute this to the pressure that the team that goes second feels because, by and large, the majority of the time, penalty kicks are successful. And so if you go first and you make that first penalty kick, the team that goes second might feel a lot more pressured because they're down, right? They're starting out down in the count. Now, again, this is a pretty well-known paper, but there is a newer paper. I think this one is in PLOS One. And in this paper, they look at many more games. Or I'm sorry, no, this is yeah. They look at many more games, and they don't just compare penalty shootouts. They start out by comparing in-game penalty kicks versus penalty kicks in shootouts. And you would think that shootouts are a more high pressure situation. Again, game is more clearly, I think, on the line. And they find, yes, there does seem to be more evidence of choking. In particular, players don't just, they're not just less successful in shootout penalty kicks versus in-game penalties, but they also miss them significantly more. So they don't just have them saved more. They actually, they go wide, or, they hit the crossbar, right? So they don't just have the goalkeeper perform better, but it seems pretty clear that players don't quite shoot as well in shootout situations versus regular time penalties. And I guess what matters for the preceding study is they find no effect of team order. And so again, that might be more updated data, things change. They also find no significant difference in conversion rates between home versus away teams. And this is going to be somewhat related to our results, because one of the things we look at is, whether a player shooting free throws is at home or not, and we do find an effect. But in this case, that there was no effect of shooting at home versus away. Although they do find home teams are awarded more penalties, which I found interesting, but I guess that's a well-known phenomenon that's been declining over time and has to do with strategic aggression or something. But anyway, that's just a curiosity. Pretty well-known paper on choking. So this is Journal of Economic Behavior and Organization by Doman. He looked at the home team advantage specifically. And so he found that players of the home team are more likely to choke. So we have a little bit of a disagreement here in terms of whether the home, being at home is an advantage or not. He seems to find a home field disadvantage where players are more likely to miss, and primarily, again, miss by missing the goal, missing the net, rather than just have it saved, when players are at home. He does not find any significant effect of attendance, which I mentioned because we do find both an effect of players shooting at home and based on the size of the crowd. He does not find one. He also doesn't find any evidence that players choke based on how close the score is, which is interesting because, as we're going to see in the next set of papers from basketball, one of the common ways we measure pressure for performance in sporting environments is whether the game is on the line. So whether your team is very close and your kick can tie or put you ahead should be a more high pressure situation than if you're down by 2 or 2 ahead. And he finds that choking rate is actually lower when the game is on the line. So players don't choke, they actually might perform a little better. Although they also find that if you're down or ahead by 3 goals or more, which means the game is, it definitely doesn't hinge on your kick alone, then the performance is even better, which I think goes back to the idea that the more relaxed players are, maybe the less impacted they are by stress. So the more confident they are, the less impacted they'll be. And then finally, we also have this last paper is a management science paper. And this one didn't just look at penalty kicks. It looked at an overall composite of player performance. And this was interesting because they looked at players performing on club teams who were eligible to make their national team in a upcoming major tournament. And what's interesting, again, for our results, because we're going to break things down by ability, they find the effects are greatest for those players who are sort of in the middle, who have a chance of making their national team, but they're not a strong favorite and they're not completely out of the running. And they actually find a positive impact on performance, right? So even though there's more on the line, these players, again, do better when they feel more pressure. And interestingly, the players who are most likely to make the national team actually see a small decrease in their performance in these games, which could be just because they don't feel they have much on the line. But again, varying effects. So, okay, coming to the results that are probably most important for our paper, since we're going to be looking at basketball. This is a paper in the Journal of Sports Economics by Cow, Price, and Stone. They looked at NBA free throws. And so they specify, we're going to consider crunch time. I think they call it crunch time, or they may call it clutch time. But the highest pressure situations in a basketball game are when we're down to the last seconds. So they primarily look at last 15 seconds, but they also look at last 30, last 60. When the game is just down by, when the team, sorry, is down by 1 or 2 points. So when the score is close, the last few seconds. And they find that there is a significant choking effect. So players who are down by 1 in the last 15 seconds of the game, so they're shooting a free throw and the game's on the line, they shoot significantly worse. And we're going to find similar effects as well. And also similar to our results, they find a varying degree of effect based on player ability. So players with more ability are less impacted by these high pressure situations. They also find effects of shooting at home, which we also find they have a very small positive effect of shooting at home. Ours is actually a little bigger. They find a very small negative effect of attendance, which again, this is going to be similar. We actually find a similar result to this as well, where free throw percentage seems to decrease by a little over 1% when attendance increases by 10,000. And these these results are also supported by another paper on NBA free throws. It's a little earlier and they don't look at as much data, but this paper by Worthy, Markman, and Maddox also looks at free throws. They get similar choking results when, players when their team is down by 1 in the last few seconds. They have a much lower shooting percentage. But they do get the interesting result that players actually shoot better when the game is tied, which, I think again relates back to the confidence idea. When the game is tied, it's, you can't lose, you can only benefit the team. Whereas when you're down by 1, I think this is just my interpretation, but it seems like the pressure is more because now you're still in the game. If you make it, if you miss, you're not. My co-author, Shane, has also been involved in a couple other papers on basketball and pressure. So one of his papers has looked at the NBA three-point shootout contest, in which players, they take 25 shots from around the three-point line. 20 of the balls are worth 1 point each, but for each location they shoot from, there's one money ball that's worth 2 points. And what they find is players shooting the money ball where, this is a pretty clear setting of, look, this shot is worth more than others, right? So that's a pretty clear, I think, implication that there's going to be more pressure on that ball. And they do find players are less successful shooting money balls. When the pressure is larger, they shoot a little worse. Shane also has this other paper with Blechner, Crow, anyway, several authors who look at NCAA data, and this is actually the same data we're going to use, and they use one of the same measures we do as the measure of pressure, which is the win probability added from making a free throw. And so we'll go into a little more about where that win probability added comes from, but it's essentially the improvement in your odds of winning if you make the shot versus if you miss it. And they find a traditional Yerkes-Dodson relationship, so an inverted U between the winning probability added of a free throw and the likelihood that the player makes it. So low pressure shots have, lower odds of being made initially. When the pressure goes up, your performance seems to increase, then past the threshold, it decreases. There's also been evidence of choking in tennis. And so in this Cohen-Zada study, they have a composite measure of how important it is to win certain break points and how that affects your probability of winning a match. They focus on gender differences, but for our purposes here, what matters is that tennis players do seem to choke under pressure. And there's also this other study by Giucciardi and Roberti, who look at ATP, again, tennis ATP tour players, and they find a positive home effect when players are, or a positive effect when players are at home. And interestingly, they don't find that crowd size is a factor. And I say it's interesting because the way they do it is they look at data from 2020 to 2022, so they compare the empty crowds during COVID versus crowds after, and they find no effect, which again is going to relate to our results because we do find an effect of attendance and a home advantage. But again, their effects are stronger for less experienced players. So this is also going to be something similar to what we find. And then last but not least, there's this is a classic paper, one of the old choking papers, Baumeister and Steinhilber. They looked at World Series games. So this is for baseball. And so the championship in Major League Baseball is a 7-game series. And usually you think the home team would have the advantage, but interestingly, although the home teams tend to win the first 2 games of a 7-game series, they actually lose the majority of games in the final game of the series, and they're even less successful on average in game 7s. And you can also look at the number of errors committed in games 1 and 2 versus the final games of the series. And again, it seems like home teams, at least in baseball, do worse, right? And so the upshot of all this stuff is that, look, there are heterogeneous effects of pressure on performance. And there's also a couple studies from basketball, this Deutscher et al. Paper and Dietl et al. They're similar. One focuses on free throws. One looks at a more composite measure of player performance in the last few seconds. Both papers find that, some players do perform better in the what they call crunch time, the last few seconds of games that are close. Some players perform better than others, and those players see better salaries, right? They are rewarded for their performance under pressure. Right? And again, we also see evidence that more experienced players in penalty kick situations tend to be less likely to choke. They're less affected by pressure. And then last but not least, and I think this still counts as sports, but there's also evidence from professional darts that, different players might perform better or worse, but overall, there's actually no significant effect of dart performance under pressure. Okay, that's a quick look at the literature on choking in sports. And so I guess the upshot is choking does seem to occur, but it's varied. And it depends how you measure pressure. And of course, it's not perhaps surprising that everyone's interpretation of pressure and how their performance response to it will be a little different in different contexts. So what we do in this paper is we begin by setting up a pretty straightforward, but tractable but interesting behavioral economic model to sort of unify the impact of distraction theories of choking and behavioral monitoring theories of choking. And what our model does is it can sort of justify different pressure performance relationships. And so we have, our model allows for both inverted U, Yerkes-Dodson pressure performance relationships, where initially higher stakes lead to better performance, but then eventually declining. And it also allows for U-shaped relationships where players initially choke, they initially don't do well with more pressure, but with enough pressure may actually do better, what we call rise to the occasion. And this is what we find in our free throw data that we think is interesting, we haven't seen before. And in the paper, we actually look at evidence from previous lab experiments. We mentioned some experiments on animals that also show clear Yerkes-Dodson relationships. But again, here for this presentation, we're primarily going to be looking at our free throw data and the impact of higher pressure on free throw performance. And this is in men's college basketball in the US. Okay. So I'm not going to go too much into the model because I know, this is not a big theory crowd, but, just to go through the idea quickly, we imagine that the probability, so we imagine someone or an agent who's set to complete some task, and the task has some reward, right? And the reward could be monetary, could be psychological. We just say they're striving to win some prize valued at V. And their probability of successfully completing the task depends. It's a ratio of their own effort and some noise parameter delta that we put in there. It's will vary up depending on the individual task, and this effective monitoring. That's this M of V. And in the model, we assume that, the influence of monitoring, so that's the overthinking part of choking, is going to increase the larger the stakes. And so the more you're worried and over-focused on your performance, the less likely you are to succeed. And we also incorporate the idea of distraction as increasing the cost of your effort. So this D of V, so your distraction is also increasing in stakes. So the higher, the prize value, the more you might be thinking about the prize value, not the task at hand. And so we're going to imagine that that's going to increase the cost of exerting effort because you're sort of wasting some of your effort on these distractions, and it's harder for you to focus. And so the agent is going to maximize their probability of successfully completing the task and earning that prize V minus their cost of effort. And so, we take first order conditions, we find the equilibrium levels of effort, we plug those back into the probability of task success, and we get this nice clean expression for the probability of an individual successfully completing their task. And what we do is we capture this effect of pressure all in one term, which we deem the pressure function, which is going to, so this falls out of as we solve the first order conditions and then plug back in the equilibrium values, this falls out, this pressure function. And so it incorporates monitoring and distraction. And so what we have in our equilibrium expression for the probability of success is, okay, your probability of success is going to be increasing in the stakes that are on the line, so that prize value V, but it's decreasing in pressure, and pressure is increasing in V as well. So there are two opposing effects. And instead of going through the model carefully, I tried to construct a basic diagram to get across. This is the intuition of the model, essentially, is, as someone's performing a task, when there is more on the line, when the stakes are larger, there are sort of two opposing forces. There's the incentive effect, which, if I do better, I'm going to be more rewarded. So that makes me exert more effort and should have a positive influence on my performance. But there's also these pressure effects, right? And whether it's distraction, monitoring, or both, those are going to counter the influence of more effort. And so the performance outcome is going to depend on both, and which effects dominate. All right, so that's the basic idea of our model. And we end up able to define what we call the stake elasticity of pressure. So the idea is, the degree to which stakes increase pressure in the athlete's mind, so to speak, will determine whether their performance improves with stakes or declines. And again, I'm not stressing the theory too much here in the interest of time, but that's the idea of the model. And so, in the paper, we go through some different functional forms and parameterizations because we want to show that, our model captures any degree or sort of a variety of relationships between pressure as measured by increased prize value or increased stakes and performance as measured by the probability of successfully completing the task. So we can have the standard neoclassical incentive effect where, more pressure leads to better performance. We can have just monotone decreasing effects. We could have the inverted U, that's the more commonly established relationship in psychology, where performance initially improves when pressure increases, then declines. And we can even find a U shape, which is what we're going to find in some of our data, and therefore we think is important to allow for, where pressure initially declines with higher stakes, but then improves as some players rise to the occasion. And so this is just sort of a very basic visual view of what our model, can capture. We can have either concave down effects. So if either the distraction component or the monitoring component of pressure, if either one of those things grows, steeply, if either one of them is convex, essentially, then we end up with a choking pattern of, stakes versus performance. On the other hand, if the distraction or monitoring effects either saturate, so they're bounded somehow, or they grow more slowly, then we're going to see what in the paper, I think we call it a rising to the occasion, but we can also call it a clutch phenomenon, where again, performance initially declines, but then finally improves. Okay, now, obviously, we can't observe this pressure function directly, right? So this is coming from our model. But what we can do is examine pressure performance, situations, look at the data, and look at the potential curvature in the pressure performance relationship. So the basic model that we're going to be looking at is the potentially quadratic impact of whatever the incentive is in a certain setting versus performance, right? So if that second parameter there, that beta 2 ends up negative, we've got the standard Yerkes-Dodson inverted U pressure performance relationship. Whereas if it's positive, we have what we call rising to the occasion, where players initially see their performance decrease, but then actually increase. Okay, and so I put this pause slide in here on purpose because I tend to be bad at making, checking if there are any questions. But are we good on questions, or do I need to pause here? Nope, I guess we're good. We're good. Okay, so we have in the paper, we pull evidence from a few different places. And as I think I mentioned, we're going to be more interested in the sports application here. But I think the other exercises are somewhat interesting just because our point is, in part, is that we see different non-monotonic relationships between pressure and performance. And so the first exercise we look at is based on a study by Ariely et al. And we're pretty sure this is a valid one. So in this paper, the authors looked at a series of lab experiments and they were done in India. And so the rewards are monetary, they're measured in rupees. And they're fairly straightforward, maybe not straightforward, but they're minor sort of, brain tasks or fine motor skill tasks. And the first one, players have to, combine shapes in a certain confined space. They call that packing quarters because they're arranging quarter circles. And another one, they play the game of Simon, which is a memory game where you tap on these lighted buttons. They have people listen to a sequence of numbers and have to repeat them. They have one of those marble games where you have to roll a marble through a maze. That's Labyrinth. They have dart ball where you have to throw a little ball at a target. So it's like darts, but with a ball with Velcro on it. And then this roll-up task where players have to manipulate a ball using these two little sticks. And so, again, so the idea here is that the authors gave their subjects varying amounts of reward. So they had a low, medium, high reward, and they looked at their performance. And what we did is so they report in their paper their means and standard deviations. And so what we do here is we just resampled assuming that data were normally distributed using their reported characteristics from their data. And we then fitted quadratic curves to the results from each task. And as you can see here, our point in this exercise is that in some cases, we do see the standard Yerkes-Dodson relationship, where performance seems to initially improve, then eventually declines. And this is probably most evident in the lower two on the left, the recall digits and dart ball tasks. The other tasks, some show somewhat of an evidence of that U-shaped performance, in particular the Labyrinth game. All right, so this gives us some early evidence that, the pressure performance relationship can both be non-monotonic and non-monotonic in different ways. All right, and then we also point to this evidence from, this is from, I want to say it's a Proceedings of the National Academy of Sciences paper. So this is a neurobiology paper where the authors trained monkeys to perform a task where they have to drag a cursor across a screen. And I'll be honest, I just think it's interesting that we can get these results to hold up in creatures other than humans. We've looked at the study pretty closely. I'll try to describe it as carefully as possible. So they verify somehow that the monkeys are aware of the reward they're going to receive. And the reward is measured in milliliters. So I think it's some kind of sweet, I don't know, nectar that the monkeys enjoy. I'm not exactly sure. But they measure how closely they can drag a cursor to a target, basically. And they do thousands of trials, but they actually do them on just 3 individual monkeys. And, the punchline is all 3 of the monkeys over thousands of trials exhibited this clear inverted U Yerkes-Dodson relationship. So at low levels of reward, we see, at least initially, there's an increase in performance. But most importantly, they have this, what they call a jackpot level reward, which is 10 times higher than, I believe, the medium reward. And for that jackpot level of incentive, they find decreased performance relative to at least the large incentive. Right. And so this shows us that, choking is not unique to humans. It's likely something, there is some neurobiological process. And in this study, the authors they seem pretty convinced that it's due mostly to explicit monitoring. And that's because they can measure the monkeys, the time they do in like the approach of the cursor. And then as they get closer to the target, do they slow down and think about it? And I guess with the jackpot level of rewards, they do. It seems to be they start thinking about what they're doing, more than maybe they should. And that's what throws off their performance. And we can't necessarily tell in our free throw data whether the choking or lack thereof is due to distraction or explicit monitoring. But again, at least some studies seem to favor the monitoring, some studies seem to favor the distraction. So that's why we have both in our model. So, okay, let's finally get to the sports portion of our paper here, or at least the sports portion of our contribution. All right, so we're going to look at free throws in basketball. So free throws are a pretty nice isolated task, right? And this is, I should mention, this is at the college level. So these are NCAA athletes, but, which I guess nowadays are professional athletes, but I can't remember if during this time period that had become a thing yet or not. But, they're serious competitive athletes. And when you're shooting a free throw, right? Although basketball is a team game, right? That free throw is a nice isolated movement, right? The other players are cleared out of the way and you're focused on that one task. So it's a pretty good test of, potential performance under pressure. Now, what we're going to do is our primary proxy for pressure is going to be this win probability added. And what we're going to do, we're going to use a metric devised by another author to look at the win probability for a given game based on whether a player makes or misses a shot. And the upshot is we end up seeming to find a U-shaped relationship. So rather than the standard inverted U, the Yerkes-Dodson relationship, we actually find a pretty clear U-shaped result where players initially see a decline in performance, which is in line with the other studies on basketball, but eventually there's a little uptick in performance. So it's not only a negative effect. And so, and this is also, it's going to vary on the players' levels of ability, experience, and we're also going to look at other measures of potential pressure, home advantage, and the size of the crowd. But win probability added is our primary metric of pressure just because that's continuous. It gives us a spectrum of pressure. And so, Shane, I don't know if you're still there, if you want to hop on and maybe talk about how we define and measure win probability added, or if you just want me to keep going through here.
Yeah, I can talk about that
Yeah.
briefly. Similar to the approach that we used in the previous paper with Bletchner and Wayne, who I think is on here. We adapted a model from Luke Benz in 2019. Luke Benz, who's a biostat PhD student at Harvard, and I've recently talked to him at Nessus about this model. But he basically, based on game state and based on score margin and just the action or the event in the game, he's able to attribute win probability added from different events and in the game. And this is really convenient for free throw shooting because in free throw shooting, you have the time's not ticking off. So the event is timeless and you just have a score contribution, a marginal score contribution or not. So we started adapting this in that previous paper that James discussed, and we've refined it a little further for this paper, but it has the same essence. Basically, if you make the free throw, the score is X plus 1 to Y, and if you don't make that free throw, it's the score is X to Y with the same otherwise same game state, same time remaining, and all of this. Yeah, thanks.
Okay, so this is going to be our measure of pressure is, how likely this shot is to, or how much, any one single free throw is going to improve the odds of winning. And as Shane explained, this win probability is a composite. It's based on the current differential, time remaining, who has the ball, various other factors. And so we're borrowing this calculation of win probability added, and we're applying it to our data. And so just to give you, I think maybe these three scenarios kind of get the idea across, right? So if we assume that the win probability is equal for any game going into overtime, right? If a game going into overtime, when the score is tied, let's assume each team has a 50% chance of winning the game. So that means if the game is tied with just 0.1 or less of a fraction of a second left, then if you make the free throw when the score is tied and there's that little time left, you're going to win. So your odds, then your win probability is going to go to 1 from that 0.5 if the game stays tied. And so in that case, we get that maximum impact of win probability added because that one shot takes you from a 50-50 chance of winning to winning for sure. Similarly, if you're down by one with less than a second left, if you make the throw, you're going to overtime. You have a 50-50 chance of victory. If you miss, you have a 0 chance of victory. So again, there is a 50% chance of free throw there's a 50% change in your win probability. Sorry about that. And then we can also think, if the other team's way ahead, if your team is way ahead, you're going to win regardless. So your shot doesn't do anything to your odds of victory. So your win probability added is 0. And the same is true if you're behind by a fairly large margin. So what we're trying to get across is, okay, the range of win probability added is theoretically between 0 and 0.5. Now, if you look at the distribution of win probability added for these, and I forgot to mention, we look at only the first free throw shot. So, typically when players get fouled in basketball, if it's a shooting foul, it's either a 1-and-1 situation where if the player makes the first one, they'll get a second shot. If they don't, they will not. Or it's just it's a set of 2 or 3 free throws. In order to get rid of the confounding factors involved in the secondary shots, we only look at the first shots that are taken. And so this is the distribution of win probability added in our data. As you can see, the vast majority of shots are not as consequential, right? And so the more consequential shots are going to be more rare. But there's still plenty of them in our data. But for the most part, they are lower. They're of lower importance, just on an average basis. So here's the summary data. So the average free throw percentage in our sample is 68.2%. You'll notice, so the average win probability added for any given shot is pretty low, right? And, the maximum value in our sample, even though it can potentially get up to 0.5, the maximum doesn't quite hit 0.3, right? But we do have a good degree of variability. We put the time elapsed there just because it indicates that a majority of the free throws in our sample seem to take place in the second half of games. College games are 40 minutes as opposed to NBA games. But look, I'm getting low on time, so I'm going to get to the results here. Okay. So remember, our primary primary pressure variable of interest is this win probability added. And what we get here is a pretty clear significant U-shaped relationship where pressure initially declines, but past a certain point, which in our data for the full sample is going to be around 0.16, performance starts to improve. And so again, this is not something we've seen previously in the literature. For the most part, in the literature, we see inverse Yerkes-Dodson relationships. What we're finding here is a U-shaped relationship. And so I should mention all these regressions include fixed effects for season and for individual players. So we're controlling for all the individual characteristics with those. We also have our basic our fundamental pressure variable is that win probability added. We also look at the impact of being at home. And consistent with the previous papers on basketball free throws that we mentioned, we find being at home has a positive impact on free throw performance. It seems to improve it by 1%. And we also look at the effect of being in a 1-and-1 situation. So again, that's where if you make the first free throw, you get a second attempt. And, we're just inferring this, but we can imagine that if you have that potential second shot opportunity on the line, that's a little more pressure. It makes that first shot a little more consequential. And what we see is there is a small effect. It's pretty small, so we don't stress the effect of the 1-in-1, but there is a significant slight decrease in performance when the player knows that, okay, if I make this shot, I can get the next one. Right? And then finally, we also look at the impact of attendance. And we're going to explore attendance a little more because we weren't expecting it to be significant, but it ends up having a significant relationship between, as a measure of, or at least what we interpret as a measure of performance or a measure of pressure on performance. But we end up, after we look at win probability added, we look at attendance a little more closely in the later part of our results, because attendance is also a potential, not, I mean, it's discrete, but it gives us a range of pressure, right? And I'll mention we measure attendance in tens of thousands, which is going to be important for the interpretation of these coefficients. But okay, so this is just the graph of based on our estimates, and I think this is based on our model 4 here, the results from the 4th column, where we do incorporate the potential impact of home, a 1-in-1 situation, and attendance. And as you can see, we've got a U-shaped relationship. At low levels of pressure, at least up until about, I think the minimum there is around a win probability added of 0.16 or 16.2. And so up until that point, more pressure, it leads to a decline in performance. But past that threshold, we do see that on average, there's this improvement in performance. And so we then break down the data. We create subsamples based on ability. So we look at each player in the sample. We only look at those players with at least 33 attempts within the sample. So we get rid of anyone who has less than that. And then we break up the sample by quintiles based on free throw percentage. And the interesting thing is that it looks like the effects of win probability added are really driven by the 4th quintile of ability, right? So it's not the worst players who see, or at least, in terms of free throw percentage, that are impacted by pressure. And it's not the best players. It's those players in the middle, which is, consistent, or at least we think somewhat consistent with previous results. So, for example, the Hickman and Metz paper, right, where intermediate levels of difficulty show the strongest effects of pressure, right? And so I guess the intuition is the players with the highest ability, they're sort of automatic, right? They don't let the pressure distract them or over monitor in those big moments. Players with lower ability, maybe, there's less to impact there. And it's the players, closer to the middle that are more impacted by pressure. And we get similar results when we break things down by experience quintile. And so here, this isn't what year in the program they are. This is based on the number of attempts they have in our sample, which is kind of a clunky measure of experience. But again, the upshot is that the influence of win probability added seems to be impacting those players in the middle. So the players that shoot way more often are less impacted, and the players that don't shoot very often are less impacted. And I'll also mention, you'll notice the magnitude of the coefficients when they are significant is significantly higher. And this is, we're gonna at the very end, and we're going through these quickly, so don't worry. I know we're running out of time, but we're also gonna compare these in crunch time versus regular time and see that the magnitude of the coefficients is going to increase substantially. Okay, so in addition to our results, just to recap the results so far, pressure does impact players' performance when shooting free throws. And it seems to have a U-shaped impact, and it seems to impact those players in the middle of the skill distribution more so than others. And so now we also decide to look at attendance. And so we don't have attendance for as many games. So that's part of the reason we didn't start out with this being our main metric. but we still have a pretty good number of observations with attendance recorded. So we can use this as potentially a measure of pressure, right? Bigger crowd, I'm under, right? Bigger spotlight, you would think there's more on the line, even if it's just psychological. And what's interesting is we find the same type of pattern between attendance and performance in terms of free throw percentage as we saw from win probability added. Right? So initially, more pressure, more people in the stands decreases performance, but eventually it's going to improve it. Right? And this is a consistent, significant result where, whether we have these extra variables included, we can include win probability added as well. So we can include both of these quadratic effects, and both remain significant, which we think is important. And our graph of attendance as a measure of pressure versus performance, free throw make probability, actually has an even more clear U-shaped pattern, right? So again, I believe this one has a minimum. It's somewhere between 25,000 spectators is where the impact goes from negative to positive. That specific value isn't important, but right, the idea is there. Now, we also we look at the effect of attendance based on ability and experience quintiles. And here, it's not exactly going against the results from win probability added, but here it seems attendance impacts those at the lower end of the skill distribution, but not just the lowest, it's sort of the lower end. And, this is true if we break the samples up into quintiles by ability, so by players' free throw percentage throughout the sample. And we get a similar result if we break things up based on experience. And so what this could be saying, and this is just our inference, but it could be that, players with less ability worry more the more people who are watching them, and maybe players with more ability or more experience, they're not as affected by the crowd, right? So maybe they're more confident, it doesn't mess with their mechanics enough. And so this is kind of getting to the role of confidence that's emphasized by Hickman and Metz. And so finally, our last empirical exercises here. So we look at the impact of both measures of performance, and we keep the home the dummy for whether the shooter is a home shooter or the away team. We keep that there because that's consistently highly significant. It's in every treatment, it seems to be the case that being at home improves your free throw percentage by 1% in college basketball for whatever reason. And here we're comparing the effects for those games in regular time. So all the way up until the last 15 seconds of regular time. We're going to refer to that as regular time versus what those previous papers we mentioned on free throw shooting deem crunch time or clutch time, the last 15 seconds of a game. And I think these results are interesting because not only are both measures of pressure significant in the same manner, the same U-shaped pattern, but the coefficients are significantly larger. And so whereas in regular time, when win probability added goes from 0, so no pressure, to 0.1, throughout regular time, it seems like there's about a 1% decline in performance for that increase in win probability added pressure. But when we're in the last 15 seconds, that impact goes up to 5 to 6%. And that's, again, consistent with what the Cow, Price, and Stone paper found for the NBA, and also the Worthy-Markman paper. Right. So the fact that we get these larger coefficients in the last 15 seconds, we think is good in the sense that it's consistent with previous studies, but we still maintain that non-monotonic U-shaped relationship. And then last but not least, we do a similar exercise where now, this comparison was only comparing games shots in regular time with shots in the last 15 seconds. We then compare shots throughout regular time with shots from overtime. And now that I think about it, I think I should have taken out the last 15 seconds of regular time here. I don't think we've done that yet. So if we do that, the results on the right might be more significant, because what we find is in regular time, the effects are similar. They're significant, but smaller in size. In overtime, they seem to be less significant, but I'm thinking maybe if we include the last 15 seconds of regular time, we'll see a difference. You'll notice, again, there's a jump in magnitude, right? So we see a larger but same pattern effect when there's more on the line, because again, we're inferring here that in overtime, each free throw would be, the player would feel under more pressure. So just to generalize our results, and I've already hinted at these, right? So we get a 1% decline in free throw shooting when we go from a win probability added of 0, meaning no pressure, to 0.1, which, remember the mean for win probability added in our sample was 0.02. It was close to 0.03, right? So this is a fairly big increase in pressure. It reduces free throw percentage by roughly 1%, depending on the treatment in regular time, but about 5 to 6% at those last seconds of the game. We also find this impact of attendance. And so again, if we start from an imaginary 0 crowd starting point to going to 10,000 spectators, we see a decline in performance by around 1 to 1.5%. And again, being at home improves performance by about 1%. So what we see here are, different types of pressure leading to different impacts, but all significant, right? So players are being impacted by pressure, but not always in any standard monotonic way. It's not always increasing or always decreasing. And so, the theoretical part of our paper, that contribution, is just to provide a model that captures these non-monotonicities that can be both hill-shaped and U-shaped. And so we didn't stress. I didn't stress the model as much in this presentation, but we think that is also a contribution. And again, the idea is, pressure, it comes in different varieties, and so it's not surprising it has different impacts. But what we think is interesting, at least in our sports data, is that we see a U-shaped impact. And of course, there are many limitations to our estimation here. And of course, there are many other ways we could measure pressure. It'd be good if we could find this sort of U-shaped relationship in other sports. But I think I've probably talked too long already here. So at this point, I'm going to stop and just open it up for questions if there are any, or if not, nevertheless, thank you for your time. I appreciate anyone who listened to me talk for this long. It's very nice of you.
Thank you very much, James. That was really very interesting to your non-basketball fan here. So thank you very much for a really great talk. We've got time for questions and comments. I should also say, you may have noticed this, my internet connection appears quite unreliable, but hopefully we can persist despite that. So I will invite folks to ask questions. Shane,
could I make one comment? Yeah, I really enjoyed James's talk, and I just wanted to mention an oversight. So the idea for like the one-on-one control, it's more of an unreported control in our study, but we actually generated the tables wrong. I did. So that's actually Wayne Grove's idea, and it involves like ongoing research with Wayne Grove. So we're going to either not control for that or represent it as an unreported control. So I'm sorry, that's my fault, Wayne. It wasn't really the point of the study, but I just wanted to mention it.
I threw it in there, but it didn't. It definitely, it's not the main pressure measure in this paper. So
so it's just going to be an unreported control. No, it wasn't James's fault, but I just wanted to mention that to Wayne because that was his, I think, a pretty seminal idea. And it won't go in the paper.
Great. Thanks, Shane. Alex has got his hand up for a question.
So thank you very much. Very nice presentation. I liked it. Just a few questions. I guess there is this problem of selection of players that go to the line at the end of the match. I'm not sure how do you deal with this, and why do you only? So I understand why. I understand the idea why you use the first shot only, because the second shot might be problematic. But I mean, how many problematic shots do you have?
Right. So I have actually run things using all of the free throws, and I can't remember every treatment, but I think the results are actually more significant and larger coefficient. I think the results might look better if we include the second shots as well, or if we just look at all shots. But to avoid any, arguments that they're not comparable, we leave them out. But our basic results hold up if we look at all shots across the board.
And the selection issue, because coaches want the ball in the last minute of the game in the hands of the best player that can perform well.
Right, so
then I'm wondering how many players really you have with the not so good performance from free throws at the
right,
end of the match.
So all right, so there's a couple answers to that. So we do control for player heterogeneity. So we control for player fixed effects, and we cluster standard errors by player. So the individual effects should be taken into account, right? But I mean, it is going to be true. The best players are those that are likely going to be in the game, especially at overtime or in those last 15 seconds. And so I guess it's interesting that we still see those choking effects for the players in crunch time, because you would think those are the players that would perform better, but they do still seem to be impacted. The other aspect, shoot, what was it? So we control for the player heterogeneity, and because sorry, I forgot the second component to your question, but I know part of the answer is the controlling for player heterogeneity, because we're interested in the effects by player. And so we also break things up by ability and experience quintile, which should also help separate those effects. So I know they're definitely there, but I don't know that they mean that what we're capturing isn't there, if that makes any sense.
Alex hasn't unmuted, so I think he's satisfied with your response.
Thank you.
So Dennis has got his hand up, and then Wayne is after that.
Thanks, James. I have two, I think, related questions. The first is, what's the mean free throw percentage in your data? And then could you show that diagram? I think it was the first plot that you did. Yeah, I think that's it. So what's the mean percentage, and where would it fall in this diagram?
Right. So the mean is 68.2%. So that's going to be about at that win probability added of 0.05, maybe.
Yeah. So if you were to draw that mean in there, what I think your diagram would show is, in the vast majority of the data, there's no difference between this effect and the mean shooting percentage. And so that gets to my second question. You said you described the results in terms of a percentage change. And I wanted to make sure, is it a percentage relative to that 0.68 or 0.682? Or is it a percentage point change? A percentage point change, that would be enormous. But a percentage change relative to 0.68 isn't very much.
No, it's a full percentage of it. It's an increase in the probability of making the free throw by 1%.
Okay.
And you're right that most, so if we look at so most of the data is actually in that 0 to 0.05 region, right? So if we look at so that the density plot here is telling us that most of the free throws are varying in that region. And so that's where the negative effects are going to be there.
Okay. I think I understand that. So then the last question is, when you described the data based on ability, how are those quintiles defined? Is that
So we look at the free throw percentage. We throw out the players who have fewer than 30 attempts in the sample, and we calculate the free throw percentage for each player who's still left over, and then we separate them by the quintiles of free throw percentage over the course of the sample.
so? Is that free throw percentage including these quote unquote high pressure shots?
Yes.
Okay. I understand. I'm sorry, I shouldn't monopolize, but the last thing about this. So my guess is, and this is an easily checkable thing, that people in that first quintile and the fourth quintile have a vastly different number of free throw attempts, even though they both have more than 30.
That could be true. I would have to check that, but that could be the case.
And so that makes me wonder if the difference here is really more one of some people are getting more shots in general than
Right.
others, and so you have a better sample on their ability for some of them than for others.
That could be the case, right? And so we also break it up by the number of attempts in the sample. And so that's this other separation into quintiles. So this is based on just the number of attempts each player has in the
Okay,
sample.
I missed that. I thought experience had something to do with minutes of playing time or something.
Yeah, no, yeah, that's my fault. I didn't go over that slowly enough because I was in a rush toward the end. Yeah, so
No
yeah,
problem.
this is the number of attempts they have.
Okay, thank you.
No problem.
Great. Thanks, Dennis. Over to Wayne.
Yeah, it's very interesting and enjoyed all this presentation. I guess don't want to be slicing the data too thin across these dimensions, but I guess the question I have is an additional component of pressure would be the significance of the game. So obviously you've got within a game, but then games really vary in terms of the significance. So perhaps in the sample, there simply aren't enough of those, to get any real purchase out of them. But some games are really determining whether or not you make tournaments, whether or not you make, postseason, you make the big game and all that. So there's probably you probably don't have enough information about those. But obviously game to game, they vary tremendously in terms of how important they are. So you've got the last 15 seconds of some games and the season's over, you've already iced it, you've won, you've lost, you don't have any chance of moving forward. It's still a game win, so not insignificant, but anyway, so that's, so what percentage do you think you would have of games overall in which the winning really matters?
That's a very good question. Thank you. It's a very good question, and it's something we've started to look at in the data because we do know we have some games in the data that are in at least early, they have those early season tournaments like the Maui Invitational, things like that. And so we're trying to figure out how can we weigh the importance of those games. Of course, ideally, if we had information just on, the NCAA tournament itself, we could look at games and earlier in the bracket versus later. But we're going to try to see, because I believe we also have information on, I think we have when the games occurred during the season. I might be wrong on that, but we'll have to go check. But we are hoping to look into that, because you're right. Obviously, some games matter a lot more. And so it'd be great to be able to compare that as a subsample to see, sort of regular season when everyone's still watching football versus springtime when everything's on the line. Yeah, that's a very good point. Thank you.
Great. Thanks, Wayne. We've got time for one more question, and Jonas has just put his hand up. So Jonas can ask that one last question.
Okay, thank you, James. I do have a bit of a clarifying question when it comes to the theory part. Sorry for not asking earlier, but I wanted to contemplate about it a little bit. So I was wondering, how exactly do you understand effort here? I currently also have a paper where we theoretically model effort in a completely different context, but I found it super difficult to think of effort as being something abstract. And there's at least two ways of, from my understanding, seeing it. There's one understanding effort in a more physical way. And if you do so, I'm wondering to what extent your delta here should be an endogenous function of effort, specifically if we're thinking of fatigue, for instance. Now, however, maybe let me try to talk about the second channel, which I believe is more relevant in the context of choking. So in choking, we are, at least from what I understand, looking at more technical tasks. And so you could probably think of effort as from a more conscious perspective. Yeah. And if you do so, then I'm wondering if then your M here that you're modeling should be an endogenous function of effort, or if the M is not exactly what effort itself should be. So I was wondering if you do have a say on that, because it seems somewhat abstract what exactly effort is in the context of choking.
Okay, yeah. So first, you're definitely right that in the model, effort is left as abstract, and it can clearly be probably either physical, mental, or both. And I guess we're probably thinking of it as both in the model, but in all honesty, do we? Okay, so backing up, I think you're right. Now that I think about it, we may want to include that E term as it may be impacting that level of monitoring. You could be that might be a good thing to put into the model. I don't know that we can disentangle it from the data. I know that some of that people have investigated in the literature, and I think more so with penalty kicks, but also I think with free throws, the impact of physical fatigue on the pressure performance relationship. And those results show, I believe, it doesn't seem like physical fatigue is a significant factor. And I guess we could try to think about that in this context, but I think it'd be tough. I think you are correct, though. It is going to be somewhat endogenous. And so we might want to at least incorporate that into the model, and I'd have to think about how to disentangle it. But it's a good point. Yeah, well made.
Okay, thank you.
Great. Thanks, Jonas. Thank you, James. Thank you, Shane. Just to say, Dennis has put a comment in the chat as we wrap up. Just ask if you compare the WPA to actual game outcomes, interested in the accuracy as a predictor of game outcomes. So that's a comment there for you to take. I'm not going to give you time to respond because I want to wrap up on time. So thank you so much, James. Thank you, Shane. That was a really interesting talk. Thank you, everyone, for your contributions in the Q&A. We will meet again this time next week when we'll have Kenneth Colombe from Bonn Graduate School of Economics, presenting racial bias and overcorrection. So thank you all once again. Wish you all a great weekend and look forward to seeing you all again soon.
Thank you.
Thanks, everyone.
Thanks, James.
Thank
Cheers,
you.
Dennis. See ya.
Thank you.